Welcome to our third lecture on fluids and temperature. This lecture deals with two equations: buoyant force, which is dVg, which is density, volume, and gravity, and the other one is AV and AV. Now, the buoyant force you might see as we said, this is rho Vg from there. The other one is an area of a pipe going at a velocity, and we're going to constrict it or expand it, and the velocity will change because of the conservation of mass through the pipe or the duct. So let's look at some example problems. So the first one says, what is the buoyant force? So there are some key words there. So if you see a buoyant force, you know you're going to use F sub B equals dVg. So the buoyant force equals your density of your liquid and the volume of the fluid being displaced, and G, and just a quick mathematical operation. And remember, force is always in newtons in our system. So here's another one. So I have a liquid at a density. It cannot exceed this much force. In other words, that's the buoyant force. That's our limit. And it says, what is the maximum volume? So we still got our equation. And so our maximum force the density of the liquid is 900, and we want the V, and G is 10, given. Now you're probably thinking, what units for volume? Well, remember back in density is a mass over a volume. So here's our mass unit in kilograms, there's our volume unit in cubic meters. And there it is. Okay, so that's pretty straightforward, I would suspect. Now let's look at the other one. Okay, we're going to constrict a pipe, or we're going to expand it, and this would be just like if you're using the water hose and you want to spray somebody. What do? You're going to stick the thumb over the end of it. What that does, that narrows your opening, makes it go out faster, because the same amount is trying to go through a smaller opening. So I got A1 V1 equals A2 V2. Okay, so you kind of put these in pairs and kind of think about it. If I constrict the opening, the velocity should increase. If I make the opening larger, the velocity should decrease. So kind of use that analogy. That'll help in figuring out if you did the right mathematical operation. So area is 5, and it does not necessarily have to be in centimeters squared or feet squared, or anything. It could be meters squared or any type of unit squared. So area, and it's going at 50. And my second area is 3, and I want the V2. Okay, the V2. You're probably thinking, okay, what is my units for V2? Look for the other units right there. Now, unless your teacher wants you to convert, just keep the same units that you started with. And you can see this one is in feet per second. And there it is. Now, this next one's a little bit trickier because I don't have an area. But I'm still constricting the pipe. So that's A1 V1 equals A2 V2. Okay. Now, you got to go back to your geometry, that the area is equal to pi r squared. Okay. Or, since I have diameter, it's pi d squared over 4. That's another way you can look at that, knowing that the radius is 1/2 the diameter, and I went on and squared the two. So the area on the first one is pi, that's 2 squared over 4, and it's going at a rate of 30 meters per second, and I'm going to constrict the flow to 1 centimeter. So that's pi 1 squared over 4. And I want to know the new flow rate. That's V2, not V squared. Be careful on that. And V2 is equal to, okay, let's look at our units. Okay, here we go. Our first one is in meters per second. And there's our units for there. And there it is. That's pretty much straightforward on these two, buoyant force and constricting pipes. Remember, if you have any questions, don't hesitate to contact me or your instructor for any help.